Okay, we learned how to calculate the confidence interval in the previous video. We only needed to calculate 4 components, and so here we are going to apply that result to a numerical example. So let's consider that an insurance company wants to estimate the expected cost of COVID treatment. Of course, the numbers are hypothetical, all made up. Uh, so suppose that an insurance company has a random sample of 100 COVID patients. And when you calculate, you observe 100 numbers, like 100 like medical expenses from 100 patients. And if you calculate average over them, you got $20,000. So on average of 100 medical expenses was to $20,000, and their standard deviation was $5,000. And from this information, so pretty simple information, but that's enough to calculate a confidence interval. So suppose that the company wants a more accurate, would like to minimize the error probability to 1%, and want a confidence level, a confidence interval with 99% confidence level. Let's see how we can do it. First, we know the formula, which is pretty simple. And X bar, let's have a look for each term, like each component. X bar is the average of X, average over 100 observations, which is 20,000. We already know that. And the standard deviation is, this is the standard deviation across 100 observations, which was 5,000, right? And sample size was 100, so its square root is 10. So already 3 components are resolved. We know them. So pretty simple. Now it remains to calculate z subscript alpha over 2. What this is. So in our example, as I said, we wanted a confidence level of 99%. That means only 1% error probability, and that means 0.5% error probability must be put each side. So we need to calculate top 0.5% value, or top 0.005 probability value. You have to find 0.995 from the standard normal distribution table or calculator. So if you do so, then you will get 2.58. So that means plus minus on the standard normal distribution, plus minus 2.58 contains 99%, right? That's how we find this number. Why we find this number. Then that's it. So we have all the numbers: 20,000, 2.58, 5,000, 10. Plug in. Pretty simple. The margin of error, first let's calculate margin of error. That is 2.58 z subscript alpha over 2 and 5,000 over square root n. So it is easy to calculate. $1,290. So this is the margin of error. So expected error, you have to allow when you have confidence level of 99%. That means the average was $20,000, but you have to add and subtract this margin of error. So in the end, your confidence interval becomes $18,710 up to $21,290. So you think the true average, the true mean, true expected treatment cost must be in between these two numbers. So, and this will be true with 99%. you have to admit that 1% probability is 1% is the error probability. So it can be wrong with 1%. So still it is under control. So we know that there can be an error, but it's only 1%. So this is how you calculate. So as you can see, derivation was more complicated, but actually application is straightforward as long as you know how to calculate this. So you may need a little more exercise to do this. So as I said, you may review chapter 6 to do that. Okay, then now I will leave it to you. Now let's change the confidence level to 90%. Now the insurance company can allow more error probability, can be more like generous to errors. And the numbers are the same, but we calculate the 90% confidence interval by yourself. Pause the video, do the algebra. And so if you have finished your algebra, let me show you the answer. So so the only difference here is everything is the same, but z subscript alpha over 2. Only this part changes when the confidence level changes from 99 to 90%. So then we know like 10% is the error probability, and that means 5% each side. So that means we are looking for a top 5% value, or 95 percentile, which is 1.64. So plus minus 1.64 contains 90% on the standard normal distribution table, right? So then using 1.64, everything else the same. Plug in 1.64 here and 5,000 square root of 100 the same. Then the margin of error is only 820. So the lower limit becomes 19 something and upper limit becomes 20 something. Simple, right? So I believe it must be easy to apply. And now let's compare what happens you change the confidence level. So like I calculated 3 different confidence intervals at 3 different confidence levels. So when the confidence level is the lowest, smallest, then the interval was actually the smallest, narrowest. But as the confidence level increases, you have to expand that interval to contain more probability. So as the probability contained in the interval increases, that's the confidence level, increase in the confidence level. So you have to widen the interval as reflected on these numbers, right? Okay, so I guess the application is pretty simple as long as you get the numbers. So I don't worry about that. But I am going to introduce another dimension. It's an interesting dimension. So we learned a trade-off, the trade-off between higher confidence level and small margin of error. You have to have small margin of error and high confidence interval, but you cannot achieve them at the same time if the data are given. But if you could include, if you could collect more data, then the story is different. You could collect more data. If you could collect more data, then you have more information, so you can improve on both sides, on both dimensions. So we will study this. Actually, the idea is simple here, but this is the starting point of experimental design theory, right? Sampling design, experiment design is a field in statistics based on this idea. Let's have a look. So in the earlier example, we considered 99% confidence interval, confidence level. At that time, at that level, the marginal error was more than $1,000. So you have to allow a large marginal error to increase the probability of correct estimation. But the insurance company may not be satisfied with this marginal error. It is too inaccurate. We'd like to make a more accurate estimator interval. Even if we need more data, we could collect, if we could collect more data, then we can reduce the marginal error. So suppose now that the insurance company wants to reduce the margin of error smaller than 500, right? So I don't want any interval greater than that. Instead, I can pay more to collect more data, right? So you collect more data as much as you want. Just give me confidence level 99% and margin of error smaller than $500. Then the question is, now those two are given. What's not given is the sample size. We can collect more data. So then our question is, okay, how many more observations do we need to improve our estimator up to this level? That is our new question, and it is not that difficult because basically the margin of error need to be smaller than 500. So this inequality, margin of error, take this form. So it should be smaller than 500. Just solve this inequality. In here, what's fixed is the error probability. The confidence level is fixed, and standard deviation also fixed. It's calculated from the data, and the sample size n is the unknown. We need to solve this inequality for sample size n, right? So alpha being 1%, like so. And then when the confidence level is 99%, this part, z subscript alpha over 2, is 2.58, which is exactly same as the earlier algebra. Of course, it depends only on the confidence level. And standard deviation was 5,000. So plug them in. You have this inequality. Now, the sample size is blank. Rearrange so that you isolate the sample size on the right hand side. Bring this to this side and bring 500 down here. So you have this, and to remove the square root, take square on both sides. So then square root n becomes just n by if you square it, and then of course you have to square the other side of the inequality. So calculate that. Easy to calculate, and then as a result you have 665.64. But of course, sample size cannot be need to be a natural number. So the decimal places don't mean anything. So you have to find the smallest natural number, satisfying this inequality. So 666 is the smallest sample size that satisfies this inequality. So you need a sample size of 666. Right? Then let me ask you the same question in another way. Like same question now, but you want to improve it even more. So the margin of error need to be smaller than $300. Previously, we considered 500. So then what is the required sample size to meet these requested conditions? Do it by yourself. Okay. If you have finished your algebra, then I will show you the answer. You use this inequality again, but here on the right hand side you have 300. So this is the same because still the confidence level is 99%. The 2.58 comes here, enters here, and by rearranging the terms, you get this, and by squaring both sides, you get this. In the end, you have 1,849, right? So as you improve your estimator, you need more and more sample size, which is the basic idea in statistical experimental design. Okay, so this is the end of this example. In the next example, I will bring the real presidential election data, like actually not the data, just results. So we will apply what we learned to the presidential election forecasting in 2012. Okay, that's in the next video. I'll see you there. Bye.